All right, so good morning, everybody. My name is Mishael. So I'm a PhD researcher at the University of Cambridge, and today I'll be presenting some of the work that we've been doing on digital fabrication and prototyping of structural ribbed concrete shells using an automated robotic concrete spraying fabrication process. So for this presentation, I'll first be going over some background and context regarding the project itself. I'll be introducing the physical robotic setup that we're using in our laboratories afterwards, a brief overview of the toolpath design, how we're actually programming the robot in order to create these components that we're using for this demonstrator, and finally some prototypes and also some 3D scan data which kind of shows the accuracy and the efficacy of the manufacturing method for producing these variable thickness thin shell structures. So this project is part of a larger UK Engineering Physical Science Research Council project called ACORN, which stands for Automating Concrete Construction. The focus is exactly as it says on the tin. We're trying to automate concrete construction. So how do we create more natural and more less prismatic forms, such as free-form beams, shelves, doubly curved structures, and how do we make that easier using digital fabrication methods? Sorry, it's all right. Using digital fabrication methods that have seen a resurgence a lot in structural and engineering practices. Here's the project team that we have. So it is spread across various universities with the digital fabrication teams held at the University of Cambridge and the computational design team at the University of Bath. So it's not just my work that's being presented here. There's a lot of people involved, and here we are. All right. So one of the main goals of the ACORN project was to see how can we recreate thin shell concrete forms. So this is the oceanographic in Spain by Felix Candela. You can see there's a lot of these very nice thin curved forms, which is very materially and carbon efficient. So that's really the aim of what we're trying to investigate. How can we create these more efficient forms to minimize material overall costs and create a more sustainable built environment? Outside of the fact that these types of structures have gone out of, well, were going out of fashion, there are some technical constraints as to why they are not being seen more nowadays. And there's two parts to that. There's the formwork construction, which is quite laborious, and it also imposes constraints on the geometry of the shell itself, and also the material deposition. It requires a lot of manual labor, a lot of traveling, all of which contributes to the fact that because we have increased labor costs by and large in most countries, a lot of these kind of forms have fallen out of use. So we're trying to kind of solve these technical issues by bringing in robotics and digital fabrication methods. The fabrication using robotic concrete spraying, we're demonstrating that through kind of a small scale setup. So here is a picture of the laboratory setup, which involves, over on the left there, a concrete sprayer for that sprays glass fiber reinforced concrete, and that is attached to a 6-axis robotic arm, which is able to move the end effector as we want it. And all of this is going to be sprayed onto a pin bed mold, which is shown over on the right there, all of which has a series of actuators which we can move to create any desirable curvature and surface profile that we want. So instead of creating multiple molds again and again, we can just simply reuse this configurable target surface and reduce the amount of labor involved in the mold process. So the configurable mold itself, it consists of 4 kind of modules which you can reconfigure. Right now it's configured into a square, and then you can see it moving up and down, but there's nothing from limiting it from being able to be connected and creating as large of a segment as you desire. Right? So this fabrication kind of process, we're attempted to kind of demonstrate the efficacy of this by creating a thin shell concrete flooring system. So this is shown on the left here, and this consists of a doubly curved shell, which was form found, that has ribs on the bottom surface. It's going to be fabricated using glass fiber reinforced concrete, and it consists of 9 segments, which are thrusting upon each other and whose horizontal stresses and horizontal thrust is resolved using these steel ties. And on the top of that, we have a false floor, which creates a level surface. Okay. So the dimensions of the demonstrator that we are constructing is 4.5 meter in span with a 55 centimeter rise. And the thickness is really what's kind of staggering with such a form such as this, because in the corners we only have 60 millimeter thickness, and at the apex it's only 30 millimeters. So it's a very thin structural form, which really goes to show how efficient shell structures are for different, as an alternative to kind of more prismatic forms. And also coupled with that, we have a very, very low structural weight of only 100 kilograms per meter square. Okay. So the shell itself, we've implemented a unique floor planning process to create the specific profile and also to lay out the ribs. And then we segmented this shell, and this is all assembled using half joint keys, which interlock with each other for assembly. All right. So that's the structural design of what we're trying to build to demonstrate this fabrication process. So next is the tool path generation. So because this is a curved surface, we need to create and slice this in a slightly different way than conventional 3D printing tool path generation. So the way that we've approached this is by leveraging the geodesic function on a variable surface, and then extracting the isolines to create evenly spaced paths. So all this does is just create paths on the surface itself on the right, which are evenly spaced regardless of the curvature of the surface that we're spraying. So this allows us to slice them in an even manner and layer them together to create whatever thickness that we want. So repeating this on a surface, we can, over there on the left, those are the input surfaces that we can define, repeating the slicing process iteratively until the full surface is captured. We get the output, which is the layered spray paths, which you can use to program the robot, and also the resulting slices and layers for the segment itself. The process that we've implemented for this two-path generation is quite flexible, and we can actually integrate lots of features. So over on the left there, we have one of the pieces that will be used to fabricate this demonstrator flooring system. And it consists of the base shell itself, which is just a flat, well, not flat, it's curved variable thickness shell with the rib features on top. And we can program the robot in order to spray different features independently. So we've included a top and bottom coat to ensure that we have a nicer finish that covers the fibers so that we don't have as many protrusions. And then the ribs itself are defined separately so that they're actually well defined. Right. So how does this all look like? Here is a video time lapse of the spraying. So it's currently spraying the bottom coating surface, and it's now spraying the internal layers in a layered fashion. So it's going back and forth in different directions. And you can see that for the further layers as it goes on, it does not spray on the far side anymore because the thickness has been attained. So we're moving towards the different areas that's required and spraying as needed. Right. So once demolded, this is how the segments look like. So over on the left is the central segment of the flooring system demonstrator. You can see that there's these unique grid-like patterns that tells the story of the digital fabrication method. It's just the same as when you're using 3D printed concrete or 3D printed anything, you'll see these striation and layers on it. It's just an artifact of the fabrication method. And over on the right there, we can see the full assembled shell consisting of the 9 segments, all assembled together on columns with the steel ties and also the false flooring on top. to just demonstrate that this is a feasible flooring system alternative. With the assembled shell, we've taken a 3D scan of the demonstrator to see how good of an accuracy we've managed to get. So we have comparing the design, the sliced, and the scanned data. You see that there's good correlation, but the scanned geometry is actually quite, in some places there's an excess thickness compared to the sliced and designed geometry that we've prescribed for this specimen. The good thing is we know why that is. Some parts are actually on purpose, so around the borders of each of these segments, we've added extra thickness in order to ensure that the structural performance of the shell is actually behaving as we want it and not underperforming. And the paths themselves, as they are generated, requires path traversals that are not fully accounted for in the calculations, so this results in extra material. The actual concrete sprayer itself is also tuned completely manually in the lab by technicians and myself, so there's some inconsistency in this setup calibration, especially the outputs, which results in variations between the segments. But all of these can be quite easily resolved, especially as we increase automation of the physical setup. So the GFRC mix that we've used, it's a standard mix that was provided to us by the manufacturer, Power Sprays. So we've used that. We didn't really adjust the mix too much, as that was not really the focus of the research project. However, it was important for us to get the material properties for modeling and testing purposes. So we've created and tested material samples along with every single one of those segments in order to evaluate the material properties. Right. All right. So after this demonstrator, we wanted to actually investigate how much can we push this fabrication method. Can we create deeper ribs? Can we create thinner members, etc.? So we wanted to test out, can we create a deeply ribbed shell that's really, really thin everywhere, so it's only 15 millimeters thick, and then at the ribs location themselves, we have a large thickness of 150 millimeters. So this is quite a highly optimized geometry, and again, the aim is to really push towards material saving and embodied carbon reduction of structures. And I unfortunately don't have a video of this one being sprayed. However, this is the demolded piece here. You can see that we've kind of achieved what we've wanted with these really defined ribs, and again, a very, very thin form everywhere else outside of these ribs. All right. Taking the 3D scans of the deeply ribbed shell and taking cross sections, you can see that there's this kind of very, very nice undulations and variation in thickness. And again, the thickness that we obtained from the manufacturing process is quite close to what we've envisioned and designed for, so we're quite happy with it. Again, obviously there's some room for improvements, but as a first pass and kind of a prototyping of this fabrication process, we're very excited to see what we can do next with it. So some conclusions. The robotic concrete spraying process that we've developed, we've tested it and prototyped it to create these variable thickness concrete shells using glass fiber reinforced concrete. We've generated these trajectory paths using unique features of a surface called geodesic functions, and then relying on their isolines to create even paths on a single layer to create even deposition. There's a lot of flexibility afforded using this method because it's not really constrained by your input geometry, so you can sequence them and add ribs, voids, whatever feature you want on top of this. However, there's some increase in accuracy that needs to be gained further by further tuning and also increased automation of the process. There's some other publications that are kind of detailing some different parts of this project because it is quite, there's a lot of different aspects. So the first one is on the spraying. The second one there is on the actual design and assembly of that demonstrator. And the last one is on the computational design and form finding. And lastly, We had a lot of project partners and project affiliates for this research project, all of which are listed here. So I would like to thank every single one of these people and also their valuable inputs throughout the research project to really help guide to where it is right now. Right. Thank you.